Master the essential programming concepts required for Cambridge A-level computer science with this comprehensive guide focused on VB.NET implementation. From fundamental algorithms like searching and sorting to advanced topics in object-oriented programming and abstract data types. This course provides clear, practical explanations and implementations of each tested concept. Whether you're preparing for exams or seeking a deeper understanding of computer science principles, this tutorial covers the important programming aspects, including linked lists, binary trees, and practical applications of algorithms that will ensure your success in A-level computer science. Moarz developed this course.
Hello everyone, my name is Moarz, and in this video we'll be talking about object-oriented programming, and then we'll talk about algorithms. So those are like binary search or insertion sort, and then finally we'll talk about abstract data types. So those are like linked list and binary trees. So yeah, I hope you enjoyed this video. The first thing you need to understand is what is a class. A class is a user-defined data type. Similar to how we have integers, strings, booleans as our data types, a class is also just another data type. But the difference is a class is user-defined, which means that we are defining this data type. So let's define a class for phones. So class phones. Notice how I define this class outside the main sub. Okay, so a class can contain two things. One, attributes, which are like just variables. And then a class can also contain methods. Methods are basically just procedures or functions. So what are the attributes a phone could have? Let's say the brand of the phone. Don't worry too much about what public means here. And then we can say public battery percentage as integer. And then we can also have, let's say, public color as integer. So we can now store the brand of the phone, the percentage of the phone's battery, and then the color of the phone. Now a class can also contain methods, right? So what are the functions that we could do on a phone? Well, let's say a phone could charge. So procedure charge. And then what this would do is this will make our battery percentage 100. Okay. Now that we have a class, we need to understand what an object is. An object is an instance of a class. So let's create an object of class phones. So let's say dim phone1 as phones equal new phones. This is how you're declaring an object. So let's say our phone 1 is a Samsung, and then its battery percentage is, let's say, 87%. And then its color is black. Yeah, let's make it black. And then let's create another object, dim phone 2 as phones equal new phones. So our second phone is a Apple. Let me just copy here. Alright. So this is phone 2. Our second phone has a battery percentage of, let's say, 65. And then its color is, let's say, yellow. So we have two objects of the class phones. Now let's say I want to charge phone 1. So first, console.writeLine, phone1 dot battery percentage. This is before we charge it. And then let's charge the phone. Phone1 dot charge. Console.writeLine, phone1 dot battery percentage. Okay, so before the battery percentage of our phone 1 is at 87%. Now after we charge it, it's 100. So yeah, that's all you need to know about classes and objects. Alright, now let's talk about accessing attributes outside the class. So here I assign values to this attribute directly outside the class. This is only possible because these attributes have a public level protection. There are several types of protection, but we're only going to focus on public and private. So when attributes have a public level protection, it means that they can be accessed outside the class directly. However, if the attributes are private, now we won't be able to access this attribute outside the class anymore. So here we have 3 attributes: brand, battery percentage, and color. And 2 of them are public, only 1 of them are private. And when you're trying to access the 2 public attributes, there's no problem. But when you're trying to access the private attribute, there's a problem. So if I run this program, as you can see, I get an error. It says that phones.brand is not accessible because it is private. So why would you even give attributes private level protection? We do that to prevent attributes from being changed or deleted accidentally. Okay, so giving attributes private level protection is safer. But then how do we access these attributes? That's where we need to use the getter and the setter methods. First, let's talk about the setter method. So let's write a procedure, sub, and then we can say set brand. This procedure will take a value as a parameter, and then we can assign the value we took as a parameter to the attribute brand. So now if we want to assign a value to the private attribute brand, instead of directly accessing it like this, we can use the setter method. So let's see. Phone1 dot, and then we can put Samsung here. Wait, let me just change this because I declared color as an integer. So color is a string. Alright, let's get back to what I was saying. Now if I run this code, I won't have any error. So here you go, there is no error. So this is a good workaround because the private attribute brand can be accessed inside the class. So by using the setter method, what I'm doing is I'm assigning the value to the private attribute without actually accessing the private attribute outside the class. So basically that's all setter methods do. They set a value to a private attribute. So we can write here, setter methods are used to set values to a private attribute. So right now I can set values to the private attribute, but I still can't access the private attribute. Let's see what I mean by this. So let's say console.writeLine, and let's say phone1 dot brand. Let's try to print this out. And we will get an error because the private attribute brand is not accessible outside the class. So in order to retrieve private attributes, we need to use getter methods. Now let's write our getter method. All we have to do is say function get brand, then we can say return brand. That's all we have to do. Now in order to retrieve our private attribute brand, instead of doing what I did here, I can call the getter method. So I can say get brand. So as you can see here, I don't get any error. Okay, so let me write it here for you. Getter methods are used to retrieve or get values from a private attribute. So I guess this is quite self-explanatory. Setter methods are used to set values to a private attribute, and then getter methods are used to get values from a private attribute. Okay, so what I want you to do now is to try and write getter and setter methods for the attributes battery percentage and color. And after you've done that, you can come here to check your answer. Okay, let's write a setter method for battery percentage first. Let's say percentage. We will take value as a parameter. Battery percentage equal value. By now, hopefully you might have noticed that all setter methods have the exact same layout. So here, if you want to set brand, you take a value as a parameter, and then you assign that value to the attribute you want to set. So if you want to set battery percentage, you take a value as a parameter, and then you assign that value to the attribute you want to set. So if I want to write a setter method for color, all I have to do is copy this and then change this to color, and then change this to color. That's it. And all getter methods also have the exact same layout. All you have to do is write the name of the attribute you want to get and then return the attribute. So let's just copy this. So here we'll say get battery percentage, and then we can just return the battery percentage. And then here we can get the color, return color. So yeah, that's it about getter and setter methods. I hope this makes sense to you. Now that we have talked about getter and setter methods, let's talk about our second special method, which is the constructor method. So the way I like to think about the constructor method is that it's just another type of special setter method. Because what does a setter method do? It takes a value as a parameter, and then it assigns the value we took as a parameter to the attribute. The only difference is that with a constructor method, we're going to take multiple values as a parameter. So let's say P brand. P stands for parameter, by the way. P battery percentage, and then P color. So when we are taking multiple values as a parameter, we need to kind of give them distinct names so that we don't get confused. Here we can just say these are values, but now we need to give them distinct names so that we don't get confused. And then all we have to do is assign the values we took as a parameter to the private attributes. So let's say brand is equal to P brand, battery percentage is equal to P battery percentage, and then we can say color is actually equal to P color. So as you can see, the only difference between a setter method and a constructor method is that the constructor method is taking multiple values as a parameter. So there's actually one more thing that makes the constructor method super special. And that is that the constructor method is called automatically when the object is being created. So this is why we use the new keyword here when we're creating the object, and then the constructor method also has the name new. And even though the constructor method and the setter method has a lot of similarities, their purpose is still kind of different. The constructor method allows you to initialize an object's attributes upon creation. So here when we are creating the object phone1, we can initialize the attributes of phone1 when we are creating the object using the constructor method. So let's say we can say here Samsung, and then we can say the battery percentage is 100 because it's a new phone, and then we can say color is black. So a constructor method is used to initialize the object's attributes, whereas the setter method is used to modify the values of the attribute after you have created the object. So let's say after we have used our phone1, we can decrease our battery percentage. Well, how do we decrease our battery percentage? That's where we use the setter method. So we can say phone1 dot set battery percentage equal 65. So I hope the constructor method makes sense to you. Okay, so now let's talk about inheritance. Before that, let's declare a class for animals. And each animal should have their age. So private age as integer, private weight as integer, and then we can also say private name as string. And then let's declare a constructor method for this class. We can say subnew, and we will take the age, the weight, and the name as a parameter. And we can say age equal A, weight equal W, and name equal N. Alright, so we have declared a class for animals. Okay, so let's add a method to our animals class. So let's say sub make noise, and then we can print out console.writeLine animal noises. So if I call this method, I will get the output animal noises. And now let's declare a class for cats. Okay, so because a cat is an animal, a cat should have all the attributes and the methods the animal class has. So one way to make this happen is to copy all the attributes and the methods from the animals class. So let's just copy all of this. But what if I added another attribute in the animals class? So what if I added, let's say, favorite color? So this new attribute will not be available in our cat class. So we have to copy and paste this new attribute too. Instead of copying all the methods and the attributes, and then copying again when the attributes change, there's a better alternative to this. We can make our cat class inherit from our animals class. Let's delete all of this, and then let's say inherits animals. The inherited class has all the attributes and the methods from the parents class. The inherited class inherits all the attributes and the methods from the class it inherits from. The inherited class is called the children's class, and then the class it inherits from is called the parents class. So there are actually other names like superclass, base class, and more, but I find the term parents class and children's class simpler because it's quite easy to imagine. This is the parent class and this is the children class, and the children inherits from the parents, just like in real life. In addition to all the attributes and the methods our children class inherits from the parents class, the children class can also have its own methods and attributes. So we can say here, private breed as string. Let me just delete this. So now the parents class only has 3 attributes. The children class has 3 attributes plus one of its own attribute. So the children class has 4 attributes. Now we can talk about how to deal with constructors in the children class. So let's put it here. 1b inheritance, dealing with constructors. As always, we can just write sub new, and then we can take the age, weight, name, and then the breed as the parameters. And then inside the constructor, we have to do something a little different. What we have to do is we have to call the parents class constructor. So we have to say mybase.new awn. So what's going to happen here is when the children class constructor gets called, the user is going to put the age, weight, name, and then the breed as the parameter. And then the children class constructor will call the parents class constructor, and then it will put the age, weight, and name as the parameter. So basically we're calling this constructor. But for the attributes we did not inherit from our parent class, like breed, we have to assign those attributes manually. So we have to say breed equal B. So again, all we're doing is we're calling the parents class constructor inside the children's class, and then for the attributes we did not inherit from the parents class, we have to manually assign them from the parameters. So let's create an object of cats. So let's say dim cat1 as cat equal new cat. So let's say our cat is 9 years old and its weight is 17 kilograms. The name it's gonna be Max, Max the bully cat. And then let's say its breed is, I don't know, British short hat, is that a thing? You know what, let's just say orange cat. Yeah, I had an orange cat once. Okay, now I have created an object of cat1 as cat. What I need you to understand is our cat class inherits from our animals class, and as you can see, there's no method called make noise in our cat class. But because our cat class inherits from our animals class, it inherits all the methods and the attributes, so we can actually use the method called make noise for our cat1. So let's say cat1.make noise, and then we get animal noises. Okay, so now let's talk about method overriding. Method overriding is when you have a method in the children class which has the same name with the method in the parents class, but they both do different things. Okay, so what do I mean by this? Let's say we have sub make noise, right? So this is a method in the parents class. I can copy this method and then I can paste this in the children's class and say sub make noise. Now a cat doesn't just make any animal noises, right? A cat makes a specific animal noise, let's say. So what I want to do is, even though our children class is inheriting all the methods and the attributes from the parents class, for specific methods with the same name, I want the children class to do something different. So for example, if I say cat1.make noise, I want it to say meow instead of animal noises. So I want it to say meow instead of animal noises. So that's what method overriding is for, to override the method. So in order to do that, I have to say here override, and then I have to write here overridable. So now if I say cat1.make noise, I will get meow instead of animal noises. So yeah, that's basically what method overriding is. So you have a method in the children class which has the same name as the method in the parents class, but the method in the children class does a different thing from the method in the parents class. So maybe we can declare a class of dogs to make things clearer. And this dog inherits from the animals class. So I'll just copy and paste the constructor. Alright. So this dog only has 3 attributes, and it inherited all these 3 attributes from the parents class. So in the children class, what we can do is we can override the parent method. We can override this method. We can say overrides sub make noise, and we can say console.writeLine bark. I'm just gonna copy this also because I don't want to waste your time. Let's say dog1 as dog, and then our dog does not have a breed, as dog equal new dog. It's dogs. Alright, so if I say dog1 dot make noise, what I will get is do you see that I call the method with the same name, but I get 2 different results? That's what I'm saying, you know, when you have a method in the children class which has the same name with the method in the parents class, but they do different things. Okay, so I promise this is the last topic about inheritance. We're going to talk about how to deal with private attributes in the children's class. Okay, let's say I want my cat to eat. So here I can say sub eat. And then each time my cat eats, I want its weight to increase by 2. So let's say each time my cat eats, I want its weight to increase by 2 kilograms. So normally the way we're going to do is we're going to say weight equal weight plus 2. But if I actually try to use this code, I will get an error, see? I hope you noticed that weight is a private attribute. So because weight is a private attribute, we can't access the attribute weight outside the class it was declared. So we can only access the attribute weight inside the class animal. So if I put here, let's say, weight equal weight plus 2, I won't have any problems. So I can access the private attribute weight only in the class it was declared in. So because weight is not declared in the class cat, we cannot actually access it directly. I just want to reassure you that the attribute weight does exist in the class cat. We did inherit the attribute weight. It's just that we cannot access them. Okay, so try to think of it. How did we used to access private attributes? I hope you remember we are going to use the getter and the setter methods. First, we need to get our weight, right? Let's say dim new weight as integer equal. We need to get our previous weight. So let's say me.getWeight. Oh wait, I don't actually have a getter method for weight here. Let me just declare it first. Function getWeight return weight. Okay, so here I can just say me.getWeight plus 2. Okay, so now that I have retrieved the value of the weight and then I have added 2, this line is basically identical with this line. So I can say this is equal to weight plus 2. Now all I have to do is assign the new weight to the attribute weight. So in order to assign values to private attribute, we have to use the setter method. We don't actually have the setter method here. So sub set weight, we'll take value as a parameter and then we'll say weight equal value. So now all I have to do is me.setWeight is actually equal to new weight. So here what I did here was I took the value of the new weight and then I use it here in a parameter. Now what will happen is weight will be equal to new weight. Weight will be equal to new weight, and new weight is equal to weight plus 2. Weight plus 2. So I hope this makes sense. I only declared a new variable called new weight so that this process seems simpler to you, but we don't actually need to declare a new variable. New weight is actually equal to me.getWeight plus 2, right? So what I can do is I can just me.getWeight plus 2 and just replace it here. So yeah, that's how I'm going to increase the weight of the cat by 2 kilograms. The only difference in using the setter method and the getter method inside the class is that here we use me dot and here we use me dot. Outside the class we will say something like animal1.getWeight, something like that. Here we use me dot, so that's the only difference. Again, one last time, me.getWeight will retrieve the value of the weight, so me.getWeight is equivalent to weight and then plus 2. And the new weight will be equal to the value in the parameter. So yeah, I hope this makes sense. So one of the 4 main principles of OOP is polymorphism. So there are 2 types of polymorphism. We have static and dynamic. Let's talk about the dynamic one first. So dynamic polymorphism is what method overriding is. And we covered this when we were talking about inheritance. So now let's talk about the second type of polymorphism, which is static polymorphism. This is what method overloading is. So this is 1, 2 or more methods have the same name but different number or type of parameters. So static polymorphism is when 2 or more methods have the same name but they have different number or type of parameters. This is not the most technical definition, but let's see what I mean by this. So let's declare a class calculators. Alright, so let's write a procedure here. Let's say sub add. and let's say x and y. So what I will do is I will print out the sum of x and y. Now let's write another method with the same name. So let's say sub add x, y, z. Okay, now we will print out the sum of three values, x plus y plus z. So here, as you can see, these two methods, right, they have the same name, but they have a different number of parameters. Here we have 2 parameters and here we have 3 parameters. So let's first create an object of this class. So dim c1 as calculator equal new calculator. So now we have created an object. Now we can say c1 dot add, let's say 10 and 15. If we add 10 and 15, we get 25. That's fair enough. Let's say now let's say c1 dot add 10, 15, and let's say 25. Now this seems weird, right? Because we actually have 2 methods which have the exact same name, but they do 2 completely different things just because they have a different number of parameters. And that's what method overloading is. It's not just different number of parameters, we can have different type of parameters also. So yeah, we get 15. So let's try one more example of method overloading. So let's say sub say hi. Now if I write sub say hi, I will just say console.writeLine hi. Now if I say sub say hi, and I will take my name as a parameter. Now console.writeLine, let's say hi, let's say 0, and then let's say name. Alright, so let's try this example. So both of these methods, they have the exact same name, but this one has no parameters and this one has a parameter. So let's say let's delete this. Let's say c1 dot say hi. Let's say c1 dot say hi Sam. Again, these 2 methods, they have the exact same name, but because they have a different number of parameters, they do different things. So that's what method overloading is. I hope this makes sense to you. Let's talk about binary search. So I have an array here, and my goal is to find the position of a number 14 in this array. I also want you to notice that this array is sorted, and that's actually quite important because binary search can only be performed on arrays that has been sorted. Here I have the algorithm for binary search, and the first step is to find the middle value. Now you and me can just look at this array and say, here, 9 is the middle value, because we can see that 9 is right in the middle. But how would a computer figure out what's the middle value? Like, what's the formula behind it? Well, the key here is to use boundary values. We can assign the lower bound to 0, and we can assign the upper bound to 10, and if we find the sum of the lower bound and the upper bound and divide it by 2, we will get the index of the middle value. So if we do 0 plus 10 divided by 2, we will get 5, and that is the index of the middle value of this array. If you don't believe me, you can count it here. 0, 1, 2, 3, 4, 5. If this part seems confusing to you, you can just ignore this for now. Okay, so we have found our middle value. It's 9. What's next? We need to now compare target with the middle value. So as you can see, our target 14 is larger than 9, our middle value. That means we have to discard the lower half. By discarding the lower half, all I mean is we are no longer going to search for 14 in this lower half region anymore. Why? Because this array is sorted, right? That means that the lower half region will only contain numbers that are smaller than the middle value. So the lower half region will only contain numbers that are smaller than 9. Right, so like 1, 3, 4, 5, 7. All of these numbers are smaller than 9. Since 14 is not smaller than 9, it is impossible for 14 to be located in the lower half region. Therefore, we are not going to waste our time searching for 14 in the lower half region anymore. But I want you to think about something. Are we only discarding the lower half region, or should we discard the lower half region including the middle value? Pause and try to think of it. Do you have an answer? If you answered, we are discarding the lower half region including the middle value, then congrats, you're correct. Again, the entire reason we're discarding the lower half region is because we know that the data we're looking for is greater than 9. So it is impossible for it to be found in the lower half region. But we also know that the data we're looking for is not 9. So the data we're looking for is not in the middle. So wouldn't it be more efficient to discard the entire lower half region, including the middle value, and search for 14 in the remaining region where it's more likely to be found? Yes, it is. So let's discard the entire thing. As we have discarded the lower half, our lower boundary changes. Moving on, what's the third step? So we have to repeat step 1 and step 2 until the target value is found or the search space is empty. Okay, so let's repeat step 1. So we have to find the middle value again. So we have found the answer. This is a binary search basically. All we have to do is find the middle value, check if the number we're looking for is smaller than the middle value or if it's larger, and then we have to either discard the upper half or discard the lower half and repeat this process until we have found the answer or until the search space becomes empty. Let's try another example. In this example, I will include the index of the array. If you don't know what this means, all this means is number 1 is located at index 0, number 3 at index 1, number 4 at index 2, and so on. Like before, in order to find the middle value, we need to find the lower bound and the upper bound. Our lower bound is initialized to 0 and our upper bound is initialized to 10. The reason our lower bound is initialized to 0 is because 0 is the index of the first element in our searchable range, and 10 is the index of the last element. In this example, I really want to emphasize the usage of the lower bound and the upper bound to find the middle index. So, as discussed previously, we add the lower bound and the upper bound and divide it by 2. So, 0 plus 10 divided by 2 is 5, and 5 is the index of the middle value. So here you go, we have found the middle value. Now let's compare target with the middle value. 12 is larger than 9, so we will have to discard the lower half. As we have discarded the lower half, we have to adjust our lower bound. Our new lower bound value is 6. And this makes sense, right? Because now the first element in the searchable range is at index number 6. What's next? Oh, we have to find the middle value again. Okay, so we have to use 6 plus 10 divided by 2. So the new middle value is at index number 8. Okay, now compare target with the middle value. So compare 14 with 12. 12 is smaller than 14. Therefore, we will discard the upper half. As we have discarded the upper half, the upper bound changes to 7. And this makes sense again, because index 7 is the last element in our searchable range. By now, I think you might have noticed a problem here. We only have 2 elements left. How do you find the middle of 2 elements? That seems impossible, you know? And it is impossible. But don't worry, let's just use our established formula and let's see where it takes us. So 6 plus 7 divided by 2. that's 6.5. And that is also a problem because there is no index number 6.5. So is this where binary search stops working? Thankfully not. So I hope you notice a double backslash here, and that double backslash is not a typo, but an indication that we're using integer division. And what integer division does is that it takes the integer component of the answer. So 6 plus 7, integer division 2, you will get 6. And our middle value is 6. And this seems very counterintuitive, but don't worry, because this method actually works, and the whole point of this example is to show you that this method works. So we get to 6, and this is our new middle value. Let's compare target with the middle value. Target is larger, 12 is larger than the middle value, so we will discard the lower half. Okay, let's discard the lower half, update the lower boundary to 7. Now let's find the middle value again. 7 plus 7 divided by 2 is 7. So we have finally found our answer using this method, which seems crazy, but it still works. And that's my point of this example. I also want you to notice that binary search is still more efficient than linear search because all we did was 4 comparisons. If this were linear search, we would have to do 7 comparisons. I'll show you. So we did 1 comparison here. We did 2 comparisons now. Now we have done a total of 3 comparisons and a total of 4 comparisons. All we did was 4 comparisons. If this was a linear search, we would have to do 1, 2, 3, 4, 5, 6, 7 comparisons. So yeah, binary search is more efficient. Okay, so let's try one last example. In this example, I'm trying to find number 13 in this array, but as you can see, number 13 does not exist. So let's use the same algorithm and let's see where it leads us. So first we'll find the middle value. Our middle value is at 9. 13 is greater than 9, so we will discard the lower half. Okay, we'll find the middle value again. Our middle value is at index 8, so it's 14. 13 is less than 14, so we'll discard the upper half. Okay, now we'll find the middle value again. Our middle value is at index 6, so it's 10. 13 is greater than 10, so we will discard the lower half. Now let's find the middle value again. Our middle value is at index 7, so 12 is our middle value. 13 is greater than 12, so we will have to discard the lower half. Now as you can see, our search space is empty, so we can assume that the number we're looking for is not in the array. Also, I hope you noticed that when the search space becomes empty, the lower bound becomes greater than the upper bound, which is quite unusual. Keep in mind of this because we can use this as a condition to check whether the search space is empty or not. Now that you know how binary search works, I encourage you to try and code this by yourself and then come back here to check your answer. So let's try the function for binary search. Function, binary search. And now we're going to take target as our parameter. So our first step is to find the middle value. And to find the middle value, you will need to find the lower bound and the upper bound. So dim lower bound as integer equal 0. Dim upper bound as integer equal myArray dot length minus 1. So the lower bound stores the index of the first element in our searchable range, and the upper bound stores the index of the last element in our searchable range. Okay? And then now, in order to get the middle value, we will need to find the index of the middle value. So dim mid as integer equal lower bound plus upper bound integer division 2. So we find the sum of the lower bound and the upper bound, and then we don't divide by 2, we actually do integer division. So be careful. This is division, like the normal division, and this is integer division. Alright, now that we have found the middle index, we can, let me just put it here. Stores the index of the middle value. Okay, now that we have the index of the middle value, we can find the middle value. The mid-val as integer equal my array mid. Now that we have found our middle value, we need to move on to the next step. So we need to compare target with the middle value. So there are three possibilities here. The first one is if target is equal to the middle value. So if target equal mid-val. If target is equal to the middle value, then we have found the data we're looking for. So if target is equal to the middle value, we can return mid. So mid stores the index of the middle value. So if target is equal to mid-val, I will return the index of the middle value. In other words, I will return the index of the data we're looking for in this array. So I hope you remember that returning anything in a function exits the function immediately. So let's say if I write any code after returning mid, console.writeLine. Hi. Do you see the code is now colored gray? This is because my IDE is warning me that, okay, I have returned something here, therefore this code will not get executed. Because after returning, we're going to leave the function. So I hope that makes sense to you. Anyway, our second possibility is if target is larger than the middle value. Else if target is larger than the middle value. Now if target is larger, then we will discard the lower half, right? Okay. So discard lower half. But how do we actually discard the lower half? What we have to do is we have to change the lower bound. Lower bound equal. So in my example earlier, for illustration purposes, I actually cut off the entire lower half. But we're not actually modifying the array itself. Because the middle index is calculated using the lower bound and the upper bound, by changing the lower bound, we can restrict the search to the upper half of the array. So by setting lower bound equal mid plus 1, we are effectively ignoring all the elements at the indices that is lower than the middle. We're effectively ignoring all of these elements. So we're only going to search for here. And the new middle index will be calculated by the new lower bound and the upper bound. So I hope that makes sense. Alright, so our third possibility is if target is smaller than the middle value. So we'll say else if target is smaller than the middle value. If target is smaller than the middle value, then we will have to discard the upper half, right? Similar to how we modified the lower bound to discard the lower half, we will have to modify the upper bound to discard the upper half. So upper bound equal mid minus 1. So if we were to discard the upper half, our lower bound would be somewhere here, and our upper bound would be mid minus 1. So this is mid, so minus 1, so it would be somewhere here. So this would be our new searchable range. So it's almost as if we cut this entire upper half off. We did not cut it, but we are restricting the search to only the lower half. So we are restricting the search to only this area. That's why I keep saying the lower bound and the upper bound defines the searchable range of our array. Anyway, so yeah, that's it. We are done with our second step. Now we need to go to our third step, which is loop step 1 and step 2 till target value is found or the search space is empty. Okay, so let's put this inside a loop. Let's say do, and loop until. So again, we have to loop until the target value is found or until the search space becomes empty. So when does the search space becomes empty? Well, the search space becomes empty when the lower bound is greater than the upper bound. Okay, so let's put this inside a loop. So we actually have two conditions to exit this loop, right? We will exit this loop when the target value is found or when the search space becomes empty. But we don't actually have to write a condition for when the target value is found, because when the target value is found, we return the middle index. So if we return something, it will exit the function. So by extension, it will exit the loop too. So we won't have to, like manually exit here. If we found something here, we won't even reach until this one anymore. It'll just exit the function. So yeah, I hope that makes sense. And then if we haven't found anything yet, we can just return -1. So the only way we will reach here is if the search space becomes empty and we haven't returned anything. So that means that if the search space becomes empty and we still haven't returned anything, it means that the target value does not exist. So yeah, let's try to test this out. Let's search for, let's say, 15. Okay, and then we'll say if return val is equal to -1, then console.writeLine target is not in the array. Console.writeLine target is at index. Okay, so let's try this out. Oh, okay. So I made a mistake here, and the mistake is I have to loop step 1 and step 2, right? So I only looped step 2. I have to loop step 1 too. I have to loop the middle value part too. So I have to put this thing in the loop too. That's why my function was not working. So yeah, let's try this again. Target is at index 3. All right, that works, right? So index 3, 0, 1, 2, 3. So we get 15. Okay, let's try with 62. Target is at index 8. Okay, that works. Let's try with 19. Target is at index 4. Okay, I'll just assume that works. Let's try with, let's say, 95. So yeah, this works. So there are so many variations of binary search. So this is just one variation, but as long as you understand the concept, you'll be able to adapt to it. But I want to show you something. So this is a do until loop, right? So we loop until the lower bound is greater than the upper bound. But if we were to use a while loop, then what we have to do is we have to loop as long as the search space is. These two conditions are completely opposite, by the way. So here we're actually looping until the search space is empty. So we're looping until the search space is empty. With a while loop, we're looping as long as the search space is not empty. So these two conditions are opposite conditions. So what we have to do is we have to do lower bound is less than upper bound. Let me just remove this one. Lower bound is less than upper bound, okay? And while this is where most people make the mistake. The opposite of lower bound is greater than the upper bound. It's not just the lower bound is less than the upper bound. We should also put an equal sign here. So yeah, make sure you don't make this mistake. Because I think it would be quite easy to like say, okay, you know what? The opposite of this is this. But yeah, don't forget to add the equal sign. If we were to use a while loop, if we were to use it this way, then we have to say the lower bound is less than and equal to the upper bound. Alright, so there's one thing important that I forgot to mention. and that is that this array has been sorted. Before you try and do a binary search on an array, make sure that the array is sorted, because you can only do binary search on arrays that has been sorted. Okay, now let's take a look at how to do binary search recursively. So here we have function recursive binary search, and you might notice that recursive binary search is very similar to iterative one. So the first thing we did was we tried to find the middle index by finding the sum of the lower bound and the upper bound and the integer division tool, and then we tried to find the middle value of the array by using the middle index. And then here our search space becomes empty when the lower bound is greater than the upper bound. So when the lower bound is greater than the upper bound, our search space becomes empty. So if our search space becomes empty and we still haven't found our data, then we can return -1. And after we have returned -1, we are exiting this recursive function. So this is our base case. Our second base case is when the middle value is equal to target. So when the middle value is equal to target, we can return the middle index and then we can exit the function. So these are our base case. Now let's talk about our general cases. If the data we're looking for is greater than the middle value, what do? Well, we have to discard the lower half, right? So we have to discard lower half. And to discard the lower half, what we did above here was we changed the lower bound to mid+1, right? So let's just copy this. If target is greater than the middle value, we discard the lower half, and to discard the lower half, we change the lower bound to mid+1. So let's copy that here. Lower bound equal mid+1. And that is exactly what we are doing here. We are calling this function recursively. So we're calling this function again, but we're changing the lower bound. Now our lower bound is mid+1. So we're taking our new lower bound as a parameter. And then if target is less than the middle value, then we will discard the upper half. And to discard the upper half, all we're going to do is we're going to change the upper bound, right? So upper bound equal mid-1, and that's exactly what we did. We just changed the upper bound. So when we're discarding the lower half, all we did was we changed the lower bound. We didn't change the upper bound or target. When we're discarding the upper half, all we did was we changed the upper bound. We didn't change the lower bound or the target. So yeah, that's all we're doing. We will call this function. We will find the middle value. If the search space becomes empty, we will stop the function and we will return -1. If we found the value we're looking for, then we will stop the function and we will return the middle index. Or else, if target is greater than the middle value, all we're going to do is we're going to change the lower bound and then we will call this function recursively. If target is less than the middle value, we will discard the upper half and then we will change the upper bound and we will call this function again recursively. So we will keep calling this function recursively until either one of these base conditions are met. So yeah, let's try to test this out. Here I can just change to recursive binary search, and our lower bound is 0. Our upper bound is my array length -1, and then our target, let's say, is 19. So let's see if this works. Target is at index 4, so 19 is at index 4. Now let's try to find 62. 62 is at index 8. Yeah, okay, 62 is at index 8. Let's try to find something that is not in the array. Let's 3627. So let's try to find this and let's see what we get. We get target is not in the array. So as you can see, our binary search function works. Let's talk about bubble sort. There's this website called visualalgo.net, and we'll be using this website to see the visualization of this entire process. Bubble sort works by comparing adjacent values, and if they're out of order, we swap them. So 24 and 8 are out of order, so we swap them. Next, we'll compare 24 and 35. They are not out of order, so we don't swap them. This process continues for each adjacent pair in the array, and after going through the array once, the largest element, which in our case is 42, reaches the end. So this completes one pass. And after a single pass, the largest element reaches the end of the array. If we repeat what we just did right now, what do you think will happen? We have gone through the array twice. So in the second pass, the second largest element gets sorted. So I think you can see where we are going here. We will repeat this again. In the third pass, the third largest element gets sorted. In the fourth pass, the fourth largest gets sorted, and so on. So essentially, all we have to do is write the code for a single pass, and then we can put that code inside a loop so that we can repeat the passes. And this will cause the entire array to get sorted. Again, let's see how this works. So this is the first pass. The largest element gets sorted. This is the second pass. This is the third pass, and so on. Alright, now let's write a procedure for bubble sort. I have a global array here, and I want to sort this array using bubble sort. So if you remember properly, bubble sort works by comparing adjacent elements, and then if they're out of order, we swap them. And we repeat this process for the entire array. So in order to go through the entire array, we will need to use a loop. So let's say for I equals 0 to my array dot length minus 2. Usually, if we want to go through the entire array, what we do is we say for I equals 0 to my array dot length minus 1, not minus 2. So I just want you to keep this in mind for now, and I'll explain why we're doing minus 2 instead of minus 1 later. So inside the array, we have to compare the elements. So we can say if my array, wait, let me just change this to j. Let me use j instead of I. My array j is greater than my array j plus 1. So if my array j is greater than my array j plus 1, what we're going to do is we're going to swap the elements. So swap them. Okay, now let's take a closer look at this part. Let's say j is equal to 0. So j is equal to 0. So when j is equal to 0, we're going to compare my array index 0 and my array index 1, right? So we're going to say my array, and then we're going to check if my array index 0 is greater than my array at index 1. So we're just going to check if 8 is greater than 24. Now let's say j is equal to 1. J is equal to 1. If j is equal to 1, all we're going to do is we're going to check if my array at index 1 is greater than my array at index 2. Now let's try to find the size of this array. So let's say console.writeLine my array dot length. Let me just add this. So the size of our array is 8, which means that the index of our last element is at index number 7. So let me just put it here. Size of array equal 8, and index of last element is at 7, which means that my array index 7 is equal to 15. Alright. So if we use myArray.length minus 1, what's going to happen is at the last iteration of this loop, j will be equal to 7. J will be equal to 7. And when j is equal to 7, what this code will result in is that my array 7, and we're going to check if my array at index 7 is greater than my array at index 8. And that's a problem because index 8 does not exist. The last element in our array is at index 7. So the largest j could ever be is 6. Right? So let's put 6 here. If j equals 6, what's going to happen is we're going to compare my array j. So my array 6. And we're going to check if my array 6 is greater than my array at 7. And this is our last comparison. The last comparison is we're going to compare 10 and 15. That's the last comparison, not 15 and something outside the array. So the size of the array is 8, and 8 minus 2 is 6. So that's what we need to do. We need to do myArray.length minus 2. So I hope that clears things up a little bit. Alright, so let's move on. Here, if the elements are out of order, we need to swap them. So how do we swap the elements? In order to swap the elements, we will need a temporary variable. So we can say temp as integer. And then we can say temp is equal to myArray j. And then myArray j, myArray at index j is equal to myArray at index j plus 1. And myArray at index j plus 1 is equal to temp. So let's try to trace this code. Here I can say that my array j is equal to, let's say, 5. And we can say that my array at j plus 1 is actually equal to, let's say, 2. So we're gonna assign the value stored in my array j to temp. So temp is now equal to 5. And then we're gonna assign the value stored in my array j plus 1 to my array j. So my array j is equal to 2. And finally, we're gonna store the value stored in temp to my array j plus 1. So my array j plus 1 is equal to 5. Okay, so now we have successfully swapped them. At first, my array at index j contains 5, but now my array at index j plus 1 contains 5, so we have swapped them. Alright, so the way I like to think of how to swap two elements in an array is by thinking of how to swap two cars. So here I have two cars, a blue car and a red car, and I want to swap them. By that I mean that I want to park the red car where the blue car is parked and park the blue car where the red car is parked. Now if I want to swap these two cars, I can just take out the blue car and then decide to park the blue car where the red car is parked. I would get a collision, right? So I can't do that. This is why if I want to swap them, I can directly assign the value from my array j to my array j plus 1 or my array j plus 1 to my array j. Either way, I'm gonna lose one of the values. Instead of this, I will have to put either of these cars in a different space. So let's take the red car and let's put it in a different position temporarily. Now that the position where I want to put my blue car is freed, I can now take the blue car and I can put it where I want it to be without causing any collisions. And then I can take out my red car from the temporary position and I can put it back where I wanted it to be. Now both of these cars have been swapped. So I hope you can see that we need the temporary variable to hold either one of the values during the swap so that we can swap without overriding either of the values. So the way I like to remember this swapping algorithm is to think that it starts with temp and then it ends with temp2. And then you can draw diagonal lines here. So I hope that makes sense. Alright, so now we have written the code for a single pass. Let me just clean this up for a while. Let me just clean all of this. Okay, so now we have written the code for a single pass. So let me just put it here. Single pass. And after a single pass, the largest element gets sorted. So 42 will reach here after one pass. Let's try and test this out. Let me delete this. And then here, I'm going to write a procedure to print. So if I call this procedure, my array will get printed. Okay, so let's say console.writeLine before, and then we can say print. And then we can just copy this actually. Copy and then paste this here. We can say console.line after first pass. After first pass. And then we can call the bubble sort here. So here we can say bubble sort. So as you can see before, this is the unsorted array, and after our first pass, the largest element in the array, which is 42, gets sorted. So if we repeat this pass again, let's try to repeat this pass again. Let's say after second pass. So now we are doing our second pass. So in our second pass, the second largest element, which is 35, gets sorted. I hope you're seeing a pattern here. If we repeat this again, let's say after third pass. So after the third pass, the third largest element, which is 24, gets sorted. So what we can do is, these are what we call passes, right? So what we can do is, we can repeat these passes for a certain amount of time until the entire array will get sorted. To repeat these passes, what we can do is we can put these passes into a loop. So let's say for I equal 0 to, let's just put 5 for now. And then we can put this in the array. So now we're going to repeat these passes. Now think about it. How many times should we repeat these passes? So my initial answer would be, if the array has 15 elements, I will repeat these passes 15 times so that the entire array gets sorted. And then if the array has 10 elements, then we have to repeat these passes for 10 times. So we will have to repeat these passes for how big the array is. My array.length -1. So we're doing -1 because we're actually counting from 0, that's why. But then let's try to think of this again. Let's say an array has 10 elements. If the array has 10 elements, and if 9 of the elements in the array has been sorted, that means that the entire array has been sorted. Because if 9 of the elements in the array are in the correct position, then the last element also has to be in the correct position. I hope this makes sense to you. Just try to think of this, and it will eventually make sense. Anyway, we can say we only have to repeat it for the size of the array -1. Actually, let's start counting from 1. So we only have to repeat from the size of the array -1. So if the array has 15 elements, we have to repeat these passes 14 times. If the array has 10 elements, then we have to repeat these passes 9 times. So let's see if our bubble sort works. So before sorting, this is our array. So 24, 8, 35, blah, blah, blah. And then after sorting, this is our array. Okay, so we can say that this works. Okay, so this bubble sort works perfectly fine, but we can make it more efficient. So let's say optimization 1. So we're trying to optimize this by trying to reduce the number of comparisons we make each pass. Let me show you what I mean by this. In our first pass, we need to compare all the elements in the entire array. And the largest unsorted element gets bubbled to the right. Let's see our second pass. In our second pass, do we really need to compare 35 with 42? We don't really need to do it. Let's see our third pass. In our third pass, do we really need to compare 24 with 35 and 42? We actually don't. With our current method, we're still comparing 24 with 35 and 42, even though we don't really need to. Because again, with each pass, the largest unsorted element gets bubbled to the right, which means that with each pass, the number of comparisons we need to do reduce by 1. So let's see here, okay? So in the first pass, we need to compare through the entire array. In the second pass, we need to do one less comparison. We don't need to compare 35 with 42 anymore. In our third pass, we don't need to compare 24 with 35 and 42 anymore. So the number of comparisons we need to do reduced by 2. In our fourth pass, I guess you can say that it will reduce by 3 and so on. So we can make our program more efficient. So we can say, since the largest unsorted element gets sorted with each pass, the number of comparisons we need to do also reduced by 1. So coding this is pretty straightforward. All we have to do is we have to say dim counter as integer equals 0, and then we can subtract the counter from the loop. So we can put a bracket here, and we can say minus counter. After that, we have to increment the counter. So after that, we'll say counter equal counter plus 1. Okay, so in our first pass, when j is equal to 0, counter is also equal to 0 because counter is initialized to 0, which means that in the first pass, we're actually comparing with every single element in the array. When j is equal to 1, it means that we are in our second pass, and in our second pass, counter is equal to 1, which means that we're reducing the number of comparisons we make by 1. So in our third pass, counter will become 2, and we will reduce the number of comparisons we make by 2. So yeah, I hope that makes sense. With each pass, we're reducing the number of comparisons we make. So this is our first optimization. Let's see if it works. So let's try and test this out. It doesn't. Why does it not work? Oh, it doesn't work because we have to increment the counter. Oh yeah, okay, I know why this doesn't work. It doesn't work because we have to increment the counter after each pass. This is a single pass, right? So only after each pass we have to increment the counter. We cannot increment the counter here. We have to put the counter here so that it increments after each pass. Okay, now that we have fixed our bug, let's try to see if it works or not. Alright, so now it works. See, 3, 8, 10, 15, 17. So I hope this makes sense to you. Our first optimization is we're reducing the number of comparisons we make with each pass. Alright, so now let's talk about our second optimization. So let's say optimization 2. Oh, and by the way, the reason I'm making all these optimization in stages is because it's important for you to know all the versions of bubble sort. So in our second optimization, we're trying to target partially sorted arrays. Okay, so let's see. We have done one pass. So the size of this array is 10. With our current version of bubble sort, we will be doing 9 passes because we have 10 elements and 10 minus 1 is 9. So we'll be doing 9 passes. But let's see if we really need 9 passes. This is our fourth pass. But I hope you noticed that after our fifth pass, we can stop sorting. So before, what we did was, we didn't check if our array has been sorted or not. We just blindly repeated the passes for n minus 1 times, where n is the number of elements. So now what we should do instead is, after each passes, we should check if the array has been sorted. So this is our first pass. After this pass, we should check if the array has been sorted. Well, it's not, so we will continue our next pass. And in the next pass, we should check if the array has been sorted. It's not, so we should do it again, and then again. But now in our last pass, how do we know the array has been sorted? I can just see this, but how could I code this? Try to look at our last pass again. What do you notice about the last pass? I will show you the second last pass. So this is our second last pass. And this is our last pass. What difference did you notice? I hope you noticed that in the last pass, there was no swaps. See, in the last pass, there was no swaps. So all we need to do is we need to check if any swaps were made in the previous pass, and if no swaps were made, then we can assume that the array has been sorted and we can stop repeating the passes. So let me just write this down. So optimization 2 reduces the number of passes. So instead of blindly repeating the passes for n-1 times, where n is the number of elements in the array, what we can do instead is we can say check after each pass if the array has been sorted. If the array has been sorted, stop repeating the passes. So this is a condition. If the array has been sorted, stop repeating the passes. Condition. And how do we know if the array has been sorted? Well, we know the array has been sorted if there were no swaps made in the previous pass. So no swaps made in the previous pass. So coding this is actually pretty simple. So below dim counter, we can declare a flag. We can say dim swap. And then we're going to declare this as a Boolean variable, so Boolean. And then I will initialize this as true. And then before repeating each pass, I'll say swap equal false. So this is the code for the pass, right? So within each pass, if I need to swap the elements, I will visit this. So if I had swapped them, I will say swap equal true. And then instead of using a count control loop, I can use a condition control loop. So I will only repeat the passes while swap is equal to true. So swap is initialized to true because we need to make sure swap is true for this loop to start. And then as soon as the loop starts, we will assign false to swap. If we actually did make any swaps, swap will become true, and then we will repeat this loop. And then swap will become false. And if we didn't make any swaps in the previous pass, swap will not become true. It will remain false. Now we're no longer repeating passes. So I hope this makes sense to you. So this is our second optimization. We reduce the number of passes we repeat. And then our first optimization is to reduce the number of comparisons we did. So yeah. Okay, so now let's talk about how we can sort 2D arrays using bubble sort. I know you guys are probably sick of bubble sort, but just bear with me. This is the last topic we're doing. So here's my 2D array. So here we have the names of the students, and then here we have the student ID. So what I want to do is I want to sort this array in ascending order of student ID. So this is the bubble sort code we last used. And what this bubble sort does is it sorts 1D array. Now let's see how we can adapt this so that we can sort 2D arrays. So there's only two differences between the bubble sort for 1D array and the bubble sort for 2D arrays. The first thing you need to know, what are you comparing? Are you comparing with the rows? Are you comparing with the columns? If so, which index and which index? So in our case, we're comparing the student IDs. So we can say, well, let me just put one here. What are you comparing? Here we can say students, and then I can say J. And then I can say J plus 1 and 1. So we are comparing the student ID. The student ID number is at column number 1. The name is at column number 0. So we're not comparing the name, we're comparing the student ID number. So we're actually comparing using the column number 1. And then we're comparing the column number 1 of each rows. So we're comparing, let's say, J and then J plus 1 and then J plus 1. So we're comparing the student ID of each rows. If we were to compare the name, I would put 0 here. But now we're going to compare the student ID. Another thing you need to understand is that we need to convert this into an integer because this is a string. Integer. So that's the first step. We need to check what are we comparing what with. And then the second step is to swap twice. So for a 1D array, we only need to swap 2 elements. Let's say if we want to swap 24 and 28, we only need to swap 24 and 28. But in our 2D array, if I want to swap this with this, I have to swap it 2 times. I have to swap Owen with Afsin, and I have to swap 8 with 9. And then if we were to swap Derek with Owen, I have to swap Derek with Owen, and I have to swap 7 and 8. So if we were to swap 2 times, I can just copy this here, and I can say this is temporary variable 1 and this is temporary variable 2. And let me just change all of this to students first. And students, we can say J and then 0. J0, here J0, and then also here is J0. So here we are swapping the names. After we have swapped the name, we have to swap the student ID. So here let's say swapping the student ID. Let's say 1, and then here we have to put also 1, and let's put 1 here also. This is almost complete. Now all I have to change is this one. For that, let's just declare a variable, dim number of students as integer. So what I can write here is I can manually count and I can put 8 here. Alternatively, what I can do is I can say students dot get length, and I can put 0 here. So if I write students dot get length 0, because we have 8 rows, I will get 8. If I write students dot get length 1 instead of 0, then because I only have 2 columns, I will get 2 columns. Okay, so all we have to do is replace this with num students, and that's it. It's actually quite a simple adaptation if you think about it. Now I'll just copy and paste the procedure to print this. So this will print the students. So let's try to call this procedure. So let's say console.writeLine before, and I can put like this here. And then I can call print here. So I will print the students before. And then let's just copy this again. After. No need for this. And then we can call bubble sort. Okay, I hope this works. Oh, there's 7 errors. That's insane. Number of indexes exceeds the number of dimensions of the index array. What's there? Oh, here. Okay. Item 1 is string. and then temp2 is also a string because these are string values. And now our array has been sorted in the ascending order of the string ID. Let's talk about insertion sort. Here I have a divider, and what it does is it separates the sorted section from the unsorted section. Since we haven't started sorting yet, we can assume that all these elements are unsorted. So we have 5 unsorted elements and 0 sorted elements. Alright, so let's start sorting. Here I have the algorithm for insertion sort, and the first step is to assume that the first element has been sorted. So we have to assume that 29 has been sorted. Let's move on. So now we start from our first unsorted element. Extract the first unsorted element, and then we will compare 10 with the sorted elements. So let's compare 10 with 29. Is 10 less than 29? Yes, it is. So we will have to shift 29 one position to the right. Now we have no more elements to compare 10 with, so we can put 10 right back here. So this is our first pass, and after our first pass, 2 elements have been sorted. Let's move on to our next pass. So we need to extract our first unsorted element, which is 14. Now we have to repeat what we did earlier, which is we will compare 14 with the sorted elements. So let's compare 14 with 29. Is 14 less than 29? It is, so we will move 29 one position to the right. Now we will compare 14 with 10. Is 14 less than 10? It is not. So we won't have to move 10 one position to the right, and we can insert 14 here. So we have completed our second pass, and now 3 elements have been sorted: 10, 14, and 29. So with each pass, the number of sorted elements grow by 1. Now let's move on to our third pass. So let's take our first unsorted element, which is 37. Let's extract it. Is 37 less than 29? So we don't need to move 29 one position to the right. And if 37 is not less than 29, we won't have to check with other unsorted elements anymore. In other words, we won't need to check if 37 is less than 14 or 10 anymore. Because this section is sorted, we can assume that if 37 is not less than 29, it is impossible for it to be less than numbers that we know to be less than 29. Another way to think of it is we only need to keep checking until we have found the first sorted element that is less than our extracted element. So we only need to keep checking until we have found the first sorted element, which is less than 37. So yeah, we can just put 37 right back here. So let's move on to our next unsorted element, which is 14. Let's extract it. And as always, let's compare it with the elements in the sorted section. So let's compare 14 with 37. 14 is less than 37, so we move 37 one position to the right. 14 is less than 29, so we move 29 one position to the right. Now 14 is not less than 14, so we can just put 14 right back here. And that's it. All elements are now sorted. So essentially, that's what insertion sort is. With each pass, it puts the next unsorted element into its correct position, whereas with bubble sort, we will bubble the largest element to the right. Let's see what I mean by this. So here, first we start from the second element because we assume that the first element has been sorted. And in our first pass, what we will do is we will put 10 into its correct position. So we'll put 10 here. If this was bubble sort, in the first pass, we won't try to put the next unsorted element into its correct position, but we will try to bubble the largest element to the right. I'll show you. So this is bubble sort, and this is the largest element. So in the first pass, we will bubble the largest element to the right. See what I'm saying here? So in the second pass, as you may have guessed, we will put the next unsorted element into its correct position. So 14 into its correct position. There you go. In the third pass, we will put 37 into its correct position. Now 37 is already in its correct position, but we still need to somehow check that it is in its correct position. Okay, now our last pass, we will put 14 where it belongs. So here you go. That's how insertion sort works. Whereas with bubble sort, we put the largest element to the right. Alright, so now let's try the procedure for insertion sort. Now if you remember the algorithm correctly, the first thing we did was to assume that the first element has been sorted. So we start from our first unsorted element, and then we try to put that in the right place, and then we move on to the next unsorted element, and then we try to put it in the correct place. So that means we need to use a loop, and our loop should start from the first unsorted element. So here, for I equal 1 to my array dot length minus 1. So I in this context stores the index of the current element we are considering. So let me just write it here. I stores the index of the current element we are considering. And the reason we start from 1 instead of 0 is because 10 is at index number 1. And we start from our second element because we assume that the first element has been sorted. So we start from our second element, which is also our first unsorted element. Now what we have to do is we have to extract the current element. So let's say dim current element as integer equal my array at I. So I stores the index of the current element, and now we have saved the current element into the variable called current element. And then what I'm going to do is I'm going to declare another variable, say dim position as integer, and I will assign I to position. So position also stores the index of the current element we're considering. We can copy this here. Okay, so now what we have to do is we have to check if the current element is less than the elements in the sorted section. So to do that, we can say while current element is less than my array position minus 1. So what position does is that it stores the index of the current element. So if I say position minus 1, then if this is the current element, then this is position minus 1. So all we are doing here is we're checking if the current element is less than the elements in the sorted section. And if it is, we have to shift the sorted elements one position to the right. So if 10 is less than 29, we have to shift 29 one position to the right. So we can say my array position equal my array position minus 1. So what this line of code does is that it shifts the sorted elements one position to the right. And then we have to decrement position. So if you're wondering why we decrement position, let's say our current element is 14. Before we start this loop, position will also be pointing to this index. Now at the start of the loop, we will compare our current element with the element one position to the left. Let's say this would be the divider, let's say. Now we'll compare 14 with 10. After we have compared 14 with 10, we can't stop there. We need to keep comparing. So what we will do is if I do position minus 1, then I will now compare 14 with 29. So that's the reason we decrement position, so that we can compare with all the unsorted elements. But we also need to stop comparing when there is no more elements left to compare with. So right now, the way this loop works is that we're never gonna stop comparing. I'll show you what I mean by this. Let's say 10 is our current element. Okay, so if 10 is our current element, then our index, our position, is at index 1 because position stores the index of the current element. So first we're gonna compare current element, and then we're gonna compare the element at the index of position -1. So we're gonna compare element at position 0, right? Because position -1. So we're gonna compare 10 and 29. That works. And then we're gonna do the necessary shifting. And then after that, we're gonna decrement the position. Now position is gonna be 0. Position is gonna be 0. And this loop hasn't stopped yet. Now what we're gonna do is we're gonna compare current element with the element at the index of position -1. So we're gonna compare 10 with the element at index -1. That's a problem, right? So we need to add a condition to stop this loop when there's no more elements left to compare with. In other words, we can say that only continue the loop as long as there is elements to compare with. So we can say that and position is greater than 0. When position is greater than 0, the smallest integer position can be is 1. So 1 is the smallest integer position can be. And that works, right? Because when we try to do position -1, 1 minus 1 is 0, and index 0 does exist. So yeah, I hope that makes sense. So now we can move on. After we have shifted the elements and when we have found the correct position, we need to insert the current element back into its correct position. So we can say myArray.position equal current element. This will insert the current element into its correct position. The reason we actually need to insert the current element back into the array is because here we're shifting the elements. We're not swapping them. Let me show you an example. Let's say we have 29 and then 10. What this code is gonna do, it's not gonna swap them. It's not gonna make it like 10 and 29. This is swapping. Code is doing, okay? This is not what our code is doing. What our code is doing instead is it's shifting. So what it's gonna do is it's gonna move 29 one position to the right. So what it's gonna do is it's gonna do something like 29 and 29. This is what this line of code does. So after we have shifted everything, what we have to do is we have to insert the current element back into its correct position. So what this line of code will do is that it will put the current element, which in our case is 10 right now, and it will put it in the correct position. This is the reason we save the current element in a current element variable at the start, because we know that the current element will get overwritten when we're shifting, so we will need to save it so that we can insert it back. So I hope that makes sense. And you might be wondering, how does position magically knows the index of the correct place to insert the current element? Well, that's because after each shift, we're decrementing the position. And because of that, position knows the correct index of where to insert the current element. So let me just clean this up a little bit, and yeah. So that's it about insertion sort. So instead of shifting the elements, the textbook uses a swapping algorithm here, but I've seen in the past papers that they use this shifting algorithm. Okay, so let's try to run this code. So let's say call insertion sort. It says that index was out of the bounds of the array. Okay, so try to think of it. We specifically added this condition so that index does not get outside the bounds of the array. So why am I still getting this error? The problem here is we are checking this condition before this condition. Now let's say our position is equal to 0, okay? Position equal to 0. So if position is equal to 0, we would have looped this the last time, and we're gonna loop this again. And when we're trying to loop this again, the first condition we check is we're going to check this condition. So we're going to check if the current element is less than the element at the index of position -1. So we're trying to check if the current element is less than the element at the index of -1. But again, index -1 does not exist. And in order to prevent this form of checking, we specifically included this condition. But the problem is we're actually checking this first. And when we're trying to check this, that's where we're getting the error. Instead, if I place this condition at first, so if I place this condition here, somewhere here, and then use AND, let's write this down here. So this is condition A. And this is condition B, okay? So what we're gonna do right now, when position is equal to 0, is we're gonna check, is position greater than 0? Well, it's not, right? So we get false here. False and whatever is false. I hope this makes sense. False and true is false. False and false is false. So what's gonna happen is, if condition A is false, if position is not greater than 0, we are not even going to try to check this condition. So this should prevent our index out of the bounds error, shouldn't it? Oh, okay. We're still getting it. Why is this? Let's say if I wrote this in Python. Then Python would do something, what I said here. It will try to check condition A, and if condition A is false, it won't check condition B anymore. This is like a quirk of VB.NET that when you write AND, even if condition A is false, it's still going to check condition B. It's pointless, I get it. If condition A is false, then whatever the condition B is, this is going to be false. But even if position is not greater than 0, even if this is false, it's still trying to check this. And when it's trying to check this, that's where we get the index out of the bounds error. So what we can do instead is we can write here and also. If I write and also, if condition A is false, it won't check condition B anymore. So I hope this makes sense. Now we should not get any errors. And there you go, no errors. Okay, so let's try to print this array. Let me just copy paste the procedure to print the array. So let's call this procedure before we have sorted. So let's say call print. And then let's try to sort it, insertion sort. Console.writeLine. And then let's print it again after we have done the insertion sort. So print. Okay, so let's see it. So here, as you can see, before we have sorted, it's 29, 10, 14, 37, 14. And then this is after we have done our insertion sort. So as you can see, our code works. One of the way I like to remember this insertion sort, because in the exam, right, you don't have time to think, what does position do? Well, it stores the index of the current element. So what should I do? Should I decrement it? Should I increment it? Like you don't have time to sort of build this up from scratch. So what I like to do instead is I try to see a pattern here. All of the lines in the loop ends with position -1. So as you can see here, it's position -1. Here it's position -1. So here it's position -1. So one quick way of remembering it, oh, you know what? It's all position -1 at the right. Yeah, I hope this makes sense too. Alright, so now let's try to adapt this insertion sort algorithm so that we can do it on 2D arrays. So first, let me declare a 2D array. So this is our 2D array, it's named jobs, and then here we have the name of the employees, I guess, and then this is the job priority. So I adapted this from one of the past paper questions, but I think in the past paper question, they use integers here. I think it's called employee number or something. But I feel like if it's employee name and then their job priority, it would be easier to, understand. So let me just clear all of this first. So if you remember how we adapted the 1D bubble sort algorithm into the 2D bubble sort algorithm, we only did two things. First, we check what are we comparing with. Are we comparing with the rows? Are we comparing with the column? And then after that, we did the swapping algorithm 2 times. We have to do the same here also. We need to check what are we comparing with. And then we have to shift this twice. And then we have to put the current element into its correct position twice. Alright, so first let's declare 2 current elements. So let's copy this and let's say, let's just call it current 1, and then let's say current 2. Both the name and the employee number are string, so we have to change this into string. Alright, now as current 1, we can take the employee name. So we can say jobs I, and then we can say 0. Here we can say jobs I and then 1. So I indicates the row number. So row number 0, 1, 2, 3, 4. And then the second dimension is for the columns. So this is column 0, this is column 1. So the names are at column 0 and the employee priority number is at column 1. Okay, so that's what we need to do. So now this is where the comparison part comes. Are we comparing with the current 1 or are we comparing with current 2? Well, we're comparing with the number, right? So it has to be current 2. So here we can say current 2. Now we need to say jobs and then position -1, 0. So that's good enough. Now we have to shift it twice. Let's see. Jobs position 0 equal jobs position -1 and 0. So if you notice here, this and this are almost completely identical. All we had to do was we had to indicate an extra dimension. Okay, and then now we can just copy this and then paste this here. And then we can say 1. So what this code does is it will shift the names, and what this code does is it will shift the job priority number. We can delete this, and then we have to insert it 2 times. So let's say jobs position 0 is equal to current 1, and then jobs position 1 is equal to current 2. We can delete this. So here we did myArray.length -1, but now we cannot do myArray.length -1 anymore. So we have to change our upper bound to the number of rows we have. That's because we're comparing the rows. So now we have to change this to number of rows we have. We have 1, 2, 3, 4, 5. We have 5 rows. So 5 minus 1 is 4. So we can say 4. And what else? Oh yeah, here I need to put integer, because this number is a string, so we need to put integer here. So after this, I think this is okay now. Let's try to test this out. So I will paste this and change this to 4. So first I will print the jobs and their priority number, and I will call the insertion sort. And what this insertion sort will do is that it will sort these elements in order of their job priority number. So Marcus should be on the top because Marcus has the highest priority. Actually, let's just change this to like 7. Then we can say console.writeLine, and then we can print out again. So this is before and this is after. Let's see if it works. So before we have Sam, Dean, Rowan, John, and Marcus. So 10, 9, 8, 7, 1. And then we have Marcus 1, 7, 8, 9, 10. So we have sorted them in order of their job priority number. So I hope this makes sense. Again, the reason we shifted twice and we assigned the elements twice because we want both the name and the employee number to shift. If we only shift it once, only the job priority number will shift. I will show you what I mean by that. Let's say I'm going to shift only once. So I'm not going to shift the name anymore. So here, this gets sorted, right? It's 1, 7, 8, 9, 10. The job priority number gets sorted. It's just that the names are not shifted. So now what happened was Sam is at 1, Dean is at 7, Rowan is at 8. Now let's talk about linked list. So there are 4 things that you need to know. First, how to traverse a linked list. Second, how to search for an item in a linked list. Third, how to remove an item from a linked list. And finally, how to add data to a linked list. A linked list is made up of nodes. So this is a single node in a linked list, and each node in a linked list contains 2 things: the data itself and a pointer to the next node. So like I said before, each node in a linked list has the data itself and the pointer to the next node, which means each node has 2 properties, and we will need a way to store both of these properties. To do that, we can declare a record data type. So this is how we will declare record data type in VB.NET. Now we can store the 2 properties of a node. So here we have the data, which is Sam, and then the next node pointer, which is pointing to index 3. However, a linked list has multiple nodes. So how do we store all of these nodes? Well, all you have to do is put the nodes into an array. So now at index 2, we have Rowan's node. At index 1, we have Claro's node. At index 0, we have Sam's node. At index 3, we have John's node. And at index 4, we have Marcus' node. So I hope you understand this. We're actually putting each node into an array. So this is like one node, this is one node, this is one node, this is one node. If you're wondering how we're going to initialize this, this is how we're going to do it. So linked list index 2 dot data equal Rowan. So here index 2 data is Rowan. And then linked list index 2 dot next node equal 1. I hope the fact that we're putting all these nodes into an array makes sense. Alright, so let's see how we can traverse a linked list. The index of the first node is indicated by the start pointer. So our start pointer is pointing to index 2. So Rowan is our first node. Be careful. Just because Sam is at index 0 doesn't mean that it is our first node. The first node is indicated by the start pointer. Now what comes after Rowan? Next node points to the index of the next node. So Rowan is pointing to index number 1. So the node that comes after Rowan is located at index number 1, which is Claro. Now Claro points to index number 4. So Marcus comes after Claro. And then Marcus points to index number 0. So Sam comes after Marcus. And Sam points to index number 3. So John comes after Sam. Finally, John is pointing to index number -1, which means John is the last node, as John points to the null pointer. If this were not a linked list, we will go in ascending order, which means that Sam will be our first node, and then Claro, and then Rowan, and then John and Marcus. However, in a linked list, the first node is indicated by the start pointer, and the next node is indicated by the next node pointer. First, to implement a node, we will need to declare a record data type. So, structure. And then remember, each node has 2 parts. The data part, and then the next node part. Alright, so we have declared the code for how to implement each node. Now let's put these nodes in an array. So we also have to declare a start pointer. So dim start pointer as integer. Notice how both my array and my start pointer are outside the main sub, which means that these are both global variables. Alright, so now I'm going to initialize this linked list. The start pointer points to index 2, and then okay, so I'm done initializing. The start pointer points to index 2, so it points to row 1 again, and row 1 points to index 1, so row 1 points to Claro, and then Claro points to index 4, so Claro points to Marcus, and so and so. So these are all string data types, but I think I forgot to add quotation marks, so let me just fix that real quick. Alright, and then let's put these above the main sub. And then our linked list has a size of 4. Okay, so now let's write a procedure to traverse, let's say sub traverse. So now we will need something to keep track of the index. So let's say dim I as integer. The index of the first node is indicated by the start pointer, so we'll say I equal start pointer. And now all we have to do is print the node at that index. So we can say console.writeLine linked list I.data. Okay, so because I is initialized with the start pointer, what this will do is this will print row 1. So let's see how this works. Call traverse. Now if I call this procedure, what happens is I will print out row 1. Now if we want to visit the next node, all I have to do is update the index with the next node. So I equal and then if I print this again, now the index is updated with what row 1 is pointing to. So if I print this again, I will get Claro. So let's copy this. If I do this one more time, I will get what Claro is pointing to. So I will get Marcus. So instead of copy pasting these 2 lines of code, what I can do instead is I can just put this inside a loop so that we would repeat this. So let's say while. So what is the condition for our loop? When should we stop repeating? Well, we should keep repeating until we have reached the end of the linked list. And the last node points to -1. So when I becomes -1, we know we have reached the end of the linked list. So we can say while I is not equal to -1, we can repeat this and let's copy this. So yeah, we have traversed the entire linked list. Okay, now let's write a function to search for an item in a linked list. So first we'll ask the user to input the data they want to look for. So now we will take the user input and we'll store that in target. Now searching for an item in a linked list is very similar to traversing it. This is because we have to visit every single node until we find the item we're looking for. So we can just copy and paste the code from here. Now the only difference between traversing and searching is instead of printing the node we're currently at, we have to compare if the node we're currently visiting is the same as the target. So here, let's say if target equal to linked list dot I dot data. So if the data we're looking for is the same as the node we're currently visiting, we can return the index of the node. Now, if we return anything here, it will exit the function. So we don't have to manually exit this traversal. Anyway, if the data we're looking for is not at the node we're currently visiting, then we can move on to the next node. So this is how we'll move on to the next node. Now, after we have visited every single node in the linked list and we still haven't found the data we're looking for, we can assume that the data we're looking for does not exist. So if we have visited every single node and still haven't found the data we're looking for, we can just return -1. So this is an indication that the data does not exist. So now let's call this function. So the value returned from this function will be stored here. If result is not equal to -1, we can say that target is found at index result. Okay, and if it is -1, we can say that target does not exist in the linked list. Alright, so let's try this. So let's search for Marcus. Oh, okay, I think I made a mistake here. I took this as an integer, but this is a string, right? Because our data is a string, so we have to take this as a string. Sorry. Alright, we can try this again. Okay, now we can enter Marcus. So target is found at index 4, and Marcus is at index 4. Let's try another example. Let's try Rowan. Target is found at index 2. So it works. Let's try something else. Let's say Akshat. So target does not exist in the linked list. So as you can see, this works. Let's see how we can delete an item from a linked list. So let's say I want to delete Marcus from this linked list. If I want to delete Marcus, all I have to do is make sure Claro is now pointing to what Marcus is pointing to. In other words, I have to make sure that Claro is now pointing to Sam instead of Marcus. Now, if we traverse this linked list, we will start from Rowan, and then because Rowan is pointing to Claro, we will visit Claro, and then because Claro is now pointing to Sam instead of Marcus, we will visit Sam. And then Sam is pointing to John, so we'll visit John instead. So we're never going to visit Marcus anymore. So essentially, Marcus is no longer a part of this linked list. But how do we make sure Claro is now pointing to Sam? Well, in order to do that, we need to know two things. First, we need to know the current index. The current index is the index of the node you want to delete. In other words, it is Marcus index. And then we need to know the previous index. Previous index is the index of the node immediately before the node you want to delete. In other words, it is Claro's index. All I have to do is update the pointers. So let's see what this code does. Essentially what it does is it updates the pointers, but let's break it down. So linked list current index dot next node. This is where Marcus is pointing to. So this stores Sam's index. Linked list previous index dot next node. This is where Claro is pointing to. So by assigning Sam's index to Claro's next node, we have updated the pointer. Again, all this line of code does is to make sure Claro is now pointing to Sam instead of Marcus. However, there's an edge case that you need to know how to handle. So what if I want to delete Rowan instead? If I want to delete Rowan, I can't change the previous pointer because there is no previous pointers pointing to row 1. So if I want to delete row 1's node, all I have to do is update the start pointer so that it is pointing to what row 1 is pointing to instead. This means the start pointer is now pointing to Claro instead of row 1. So when we traverse the linked list, we will start from Claro instead, and then Claro is now pointing to Marcus, so we'll visit Marcus, and so and so. This means that we'll never be visiting row 1 anymore because Claro is now our first node. So how does this affect the overall algorithm? It doesn't change much. All we have to do is first check if the node you want to delete is the first node. And if it is the first node, we have to update the start pointer. If it is not the first node, then we have to update the appropriate pointers. So we have to do what we mentioned in the previous slide. This one. So yeah, that's it about deleting an item from a linked list. Oh, by the way, if there is an empty list, we can point the last node in the empty list to the node we just deleted so that we don't waste space. Okay, so now let's try the procedure to delete an item from a linked list. So here I'll just copy paste this because I want the user to input the data they want to delete. So enter the data you want to delete. Now the first thing you need to do is check whether the data we want to delete is at the start pointer. So if linked list, start pointer dot data equal target. If the data we want to delete is the first node, then all we have to do is change the start pointer so that it is now pointing to what the first node is pointing to. So the second node now becomes the first node, if that makes sense. And then we can exit this up. If the data we want to delete is not in the first node, so we will need to know the index of the node we want to delete, and then the index of the node immediately before the node we want to delete. So in order to find that, what we can do is we can just traverse to the linked list. By now, I hope you have noticed that like all of these functions or procedures, they involve traversing to the linked list. Alright, so now I'm gonna declare a new variable and I'll call this previous. So prev. So what this variable will do is that it will keep track of the index of the node before the current node. Alright, so here I can just say previous equal I. So here before I gets updated with the index of the next node, previous will store the index of the node before the current node. Okay, so now if we have found the node we want to delete, all we have to do is update the pointers so that the previous node is now pointing to what the node we want to delete is pointing to. So all we have to do is linked list dot previous dot next node equal linked list I dot next node. So when we have found the node we want to delete, all we have to do is make sure that the node before the node you want to delete is now pointing to what the node you want to delete is pointing to. Alright, let's test this out. Call delete. Right, and then we can copy this and then paste this here. So here what we're doing is after deleting. Alright, so let's see. Sorry, here I have to put start pointer, because the new start pointer has to point to the second node, right? Yeah, okay, so I hope it works now. Okay, so this is the before deleting, row 1 Claro, Claro, Marcus, Sam, John. Let's delete Rowan. Okay, so after deleting, all we have is Claro, Marcus, Sam, and John. Okay, let's try deleting Marcus. So after deleting Marcus, all we have is Rowan, Claro, Sam, and John. So Marcus is deleted. Let's delete John then. So after we delete John, we get Rowan, Claro, Marcus, Sam. Now let's talk about how we can add a node into a linked list. So for this, I actually have two methods. The first one is the method I find more intuitive, and the second one is the method I found in the Moarz game. So I'll be showing you both, and you can decide which method you prefer. So here, it seems that we have two linked lists. The first one is our main linked list, and this holds our data. And then we have a free list, which keeps track of our unused spaces. The reason we have a free list is if you look at our array here, we have space for 5 nodes. Right, so 1, 2, 3, 4, 5. So we have space for 5 nodes, but we have only used 3 nodes. 1, 2, 3. So the free list contains the 2 unused nodes. If you're confused, this is not a separate node. This is just an indication that the last node is pointing to a null pointer. So the last node is pointing to -1. Anyway, so here we also have 2 pointers. So the start pointer points to the index of the first node of our main list, so Rowan. And then the free pointer points to the index of the first node in our free list. So the free pointer is pointing to index 3. So this is the index of the first node in our free list. I hope this makes sense. Alright, so in order to add something, our first step is to ensure that there is enough space to add. By that I mean that we have to check that there is at least one unused node. Because if there isn't any unused nodes, then we won't have any more space to add. Alright, so we're adding our new node at the end of our linked list, right? So that we have to make sure that Marcus, which is the last node of our linked list, is pointing to the first node of the unused space. So we have to make sure that Marcus is now pointing to free pointer. Now we can add the data we want to add in our first unused node. We can add John here. Oh yeah, so by the way, I hope you noticed that Marcus was previously pointing to -1, which indicates that Marcus is the last node, but now Marcus is pointing to index 3, which is the index of our new node. And now, after we have added the data we wanted to add in our first unused node, we have to update the data here. So we have to put John here. After that, we have to update our free pointer. The reason we have to update our free pointer is because this node is now used. So it's no longer the first unused node. The first unused node is this. So we have to update our free pointer to point to the index of the second unused node. So our free pointer is pointing to index 4. Oh yeah, that's a bad animation. I just assumed that this is no longer here. So yeah, our free pointer is pointing to index 4. And then we can put John here. So this is our new free list. After that, all we have to do is make sure that John is now pointing to -1. The reason we have to make sure that John is now pointing to -1 is to indicate that John is the last node. So for me personally, I prefer this method because it's easier for me to understand. As in, I can sort of just derive this method easily without having to memorize the algorithm, because this method seems more natural to me. If you prefer this method, you can use this method, but I will also show you the method that the Moarz game uses. Okay, so this is the method I found in one of Cambridge Moarz games. So first we have to check for free space. After that, we have to create a new node. And then we have to initialize that new node with the data we're going to add and make sure that new node is pointing to -1. After that, we have to place this new node at the end of the linked list. Now we can update the free pointer so that it is pointing to the second unused node. So yeah, that's the method Cambridge uses. So before, our linked list has no free spaces. I did that so that if we simplified the linked list, it would be easier to understand traversing, searching, and everything else. But now, let me change some of the values of the linked list. And then I need to declare a new pointer to point to the start of the free list. So dim free pointer as integer equal 3, because this is the index of the start of the new list. And now let me change my new start pointer. It has to be pointing to 1. Now let's write a function to add a new node. So let's just call it function add. So the first thing we need to do is to check whether if there is enough space. So we can say if free pointer equal to -1, return false. So basically, if there isn't enough space, then we would just return false. So we won't add anything anymore. Now my reasoning behind assigning free pointer to -1 is because the last free node points to -1. So after we have used the last free node, the free pointer will be updated to -1, which means that if there is no more free nodes, then the free pointer would be -1. So then we would know that there isn't enough space to add in the linked list. Now, if there is enough space, we will move on. So what we will have to do is we will have to traverse the linked list. So let me just copy a code from somewhere here. So we will have to traverse the linked list. Okay, so the reason I traversed the entire linked list is because I want to find the last node in the linked list. Find the index of the last node. So the index of the last node is stored in previous, because I is now -1, so previous stores the index of the node before the current node. So index of the last node is stored in previous. So if I say I equal previous, this means that I now stores the index of the last node. So now I have the index of the last node. So my next step is for my last node to point to the first free node. To do that, all I have to do is linked list I dot next node equal free pointer. Alright. After this, I can add the data at the index of the free pointer. So add data linked list free pointer dot data equal. Oh wait, I did not take data from the user. Let me just take data from the user. So let's say, let me just prompt that user. Okay, and then here I can say dim data to add. Data to add. So now I will take data to add as an input from the user. Okay, so this is equal to data to add. After this, I have to update the free pointer. Next free node. So before doing that, what I will need to do is I need to save the free pointer, because after I update the free pointer, I will lose the value of the free pointer. So I have to save free pointer. So I'll save this here in a temporary variable, and then I'll say now I can point free pointer to the next free node. So linked list dot free pointer dot next node. Now all I have to do is make sure the new last node points to -1. Okay, so what is the index of the new last node? Well, the index of the new last node is the index of the free pointer. Not this free pointer, but this free pointer. So we can say that value is now stored in temp. So we can say linked list dot temp in next node equal -1. Alright. Now I get that this has like so many lines of code, but again, like for me personally, it is quite derivable. So I'm not sure if this is derivable for you or not. So that's why I'm gonna show you both methods. But before I show you another method, Let's test this code out first. Let's test this. Traverse. Now I can add the nodes. Oh yeah, wait. Okay, so if this was a function and I returned false here, then after I successfully added, I have to return true. So here I can say dim result as boolean. If result equal false, if result equal false, not enough space. Let's add 2 times. And then we can say after adding, and then we can write traverse. Okay, so before adding anything, we have Rowan, Claro, and Marcus. Now let's add Jamil. And then we can add Afsin. Here we get Rowan, Claro, Marcus, Jamil, and Afsin. Alright, so let me walk you through the code that I found in one of the Moarz games. So I named this function add2, and I changed some of the variable names so that it matches with this function, but apart from that, I didn't change anything else. So they first start by checking if there is enough space by checking whether the free pointer is less than 0 or whether the free pointer is greater than 9. So I'm not sure why they would check it this way, because as I told you earlier, if there is no more nodes in the free list, then the free pointer will be pointing to -1, because the last node in the free list points to -1, which means that after we have used the last node, the free pointer will be updated to point where the last node is pointing to. So the free pointer should be pointing to -1. So I guess this works, but I'm not sure why it's greater than 9. Maybe it's because it's the size of their array. Anyway, after that, what they did here is they created a new node, and then they initialized the new node with the data to add, and it is pointing to -1. And after that, they placed the new node at the index of the free pointer. Okay, that's cool. And then now they're trying to find the index of the last node. So let me just put a comment here. Trying to find the index of the last node. And then I think previous stores the index of the last node. So previous stores the index of the last node. So I think this is their form of temporary variable. So they made a new temporary variable and make sure that the temporary variable is now pointing to the free pointer. Okay, that's good. Now the last node points to the free pointer, and at the index of the free pointer, we have this new node. That makes sense. There is one problem with the code that I noticed. When they update the new free pointer, they are doing it incorrectly. Because here they say that the free pointer equal linked list free pointer.next node. But the problem is, wait, let me show you. Linked list free pointer.next node. This is equal to -1. This is supposed to be the index, supposed to be at the index of the second node, but it's not. This is -1, because when they initialize next node with -1, and then they place this whole node at the index of the free pointer, what happened was linked list free pointer.next node became -1. So there's a simple fix to their problem, and that is that you have to assign new node to the index of free pointer later. Let's copy this here and let's paste this here. Now what happens is linked list free pointer.next node is the index of the second free node. This is updated correctly. And then here we will have to put value to right here, because value to right is the index of the free pointer, which is the index of the first unused node. So now this would work. Let's try adding two data now. So let's try adding Owen, and let's try adding Ayana. Now after adding it, we get the correct addition. So maybe I am wrong here. If you can correct me, please correct me in the comments. But I think Cambridge's code is kind of wrong. And the way it is wrong is that it's hard for you to, it's hard for you to spot the error, because in their question, they only ask you to add one item. And when you only add one item, this code works fine, because you don't need the new free pointer when you're not gonna add another item. If you're like a beginner and if you've never done this, then if you're confused with this, then yeah, you should be, because I did not explain this properly to you. But there isn't enough time, so yeah. I'm sorry. If you want to ask me more on this, let's talk about binary trees. So basically, there are only two things that you need to know. First, you need to know how to insert an item into a binary tree. And second, we need to know how to find an item in a binary tree. Before we can take a look at how to insert an item into a binary tree, we need to first understand how we're going to implement a binary tree. Here I have a node, and each node contains three properties: the data itself, a left pointer, and a right pointer. So now we will need to declare a data type to store all these three properties. So what we're going to do is we're going to declare a record data type. Here's how that's done in VB.NET. So now I have a way to store all the attributes in a node. So data is row 1, left pointer is 1, and the right pointer is 2. However, a binary tree has multiple nodes. So we need to find a way to store multiple nodes. So how do we store multiple nodes? We can use an array. So as you can see here, I have put all these nodes in an array. So at index 0, we have row 1's node. At index 1, we have Dean's node. And at index 2, we have Marcus' node. So this is how we're going to assign the values. Binary tree index 0 dot left pointer is 1. Binary tree index 0 dot data is row 1. Binary tree index 0 dot right pointer is 2. This process is quite similar to how we implemented a linked list. The only difference is we have one extra attribute now. Now let's talk about how to deal with pointers. The root node in a tree is the first node in a tree. So this is the root node because this is the first node. And the index of a root node is indicated by the root pointer. So now our root pointer is pointing to index 0, which means row 1 is our root node. If the root pointer was pointing to index 2, then Marcus would be our root node. Now this is where it gets important. The pointer stores the index of a child node. What do I mean by this? Well, if you look at here, the left pointer is pointing to index 1, which means that row 1's left child is Dean. And row 1's right pointer is pointing to index number 2, which means row 1's right child is Marcus. So yeah, in a binary tree, the node that is directly below another node is called the child node. So Dean is row 1's left child and Marcus is row 1's right child. So now, Dean's left child is an index tree. So Dean's left child node is Aurora. Dean's right pointer is pointing to -1. That means that Dean doesn't have a right children. And Marcus, both left pointer and the right pointer are pointing to -1, which means that Marcus has no children, nor does Aurora. So that's all you need to know about pointers. The pointer stores the index how we can insert data into a binary tree. So this is the data we want to insert, and this is the algorithm we're going to follow. Alright, so let's start with 12. the first data that is added at the root node of the tree. So 12 will go to the root node. Okay, now let's add 5. So we will have to compare 5 with 12. If 5 is less than 12, 5 will go to the left subtree. If 5 is greater than 12, it will go to the right subtree. So because 5 is less than 12, it will visit the left subtree. Okay, now let's add 1. We will do the same thing. We will compare 1 with 12. So 1 is less than 12, so 1 will visit the left subtree. But we can't add 1 here because we already have 5 here, so we can override 5. So what we have to do is we will compare 1 with 5 again. And because 1 is less than 5, it will go to the left subtree. And here we have nothing, so we can add 1 here. Alright, let's add 17. We will compare 17 with the root node first. So 17 is greater than 12. So 17 is greater than the root node. So it will go to the right subtree. And here there's nothing, so we can add 17 right here. Now let's add 8. We will have to compare 8 with the root node first. 8 is less than 12. So 8 is less than the root node. So we will have to visit the left subtree. Now we will compare 8 with 5. 8 is greater than 5, so we will have to visit the right subtree. Now there's nothing here, so we can just add 8 here. Now our last item, 15. So we'll compare 15 with 12. 15 is greater than the root node, so we will visit the right subtree. Now we can't add 15 here, right? Because we already have data there. So what we will do is, we will compare 15 with the data at the node we're currently visiting. We will compare 15 with 17. 15 is less than 17, so 15 will go to the left subtree, and there's nothing here, so we can add 15 there. I hope this makes sense to you. It's actually quite a simple process. All you have to do is check if the data you want to add is either less than or greater than the node you're currently visiting. And if it's less than, you visit the left subtree. If it's greater than, you visit the right subtree. And you keep on going until you find an empty space and you can insert your data there. Let's try one more example. So again, we have nothing here, so we have an empty tree. So the first data that is added will be at the root node. Here you go. So 15 is at the root node. Now let's add 12. We will compare 12 with the root node. 12 is less than 15, so we will visit the left subtree. Now let's add 5. 5 is less than 15, so we will visit the left subtree. We can't add 5 here because there's 12, so we will have to compare 5 with 12. 5 is also less than 12, so we will visit the left subtree of 12. And here we have an empty space, so we can add 12 here. And then we will add 17. 17 is greater than 15, so we will have to visit the right subtree. And there's nothing here, there's an empty space, so we can add 17 right here. So yeah, I hope this makes sense to you. Alright, so now let's implement a binary tree. So to implement a node, we have to declare a structured data type. So that's a structure node. And then we can say dim left pointer as integer. We can just copy this and then let's say right pointer. Then we can say, let's say data. Alright, so we have a way of representing the left pointer, the data, and the right pointer of each node. Now we can put that node in an array. Dim binary tree. Let's say we will have 20 nodes as node. Alright, now a binary tree usually have 2 pointers. So we will have a root pointer, and this pointer is initialized to -1. This is because our binary tree is empty, but the root pointer usually points to the index of the root node. Similar to how a start pointer points to the index of the first node in a linked list, a root pointer points to the index of the root node of the tree. And then we will have a free pointer, which is the index of the next free space. So okay, after we have done this, let me just tidy this up a little bit by putting it above submain. Now let's write a procedure to insert a node into a binary tree. So let's say sub insert. So a binary tree is a dynamic data structure. However, we're implementing our binary tree using this array, and an array has a finite size. So for example, for this array, we can only add up to 20 nodes. So the first thing you have to do before adding anything is to check if there is enough space. Alright, but how would you check if there is enough space? You would check by comparing using the free pointer. So let's say if free pointer is less than or equal to 19, then it means that we have enough space. Or else we can print. No, we cannot print. We have to write console.writeLine. Or else we can write console.writeLine. Free is already full. So the first step is to check if there is enough space. So this is 1A. There is enough space. And this is the other possibility. There is no space, I guess. So the free pointer points to the index of the next free space. So if the index of the next free space is less than 19, then we know there is enough space. If the index of the next free space is 19, we know that there is enough space for one more node. If the index of the next free space is more than 19, in other words, if the free pointer is pointing to a value that is larger than 19, then there is no more space anymore. Because let's say if the free pointer is pointing to, let's say, 20, that means that the next free space is at index 20. But the largest possible index of an array is at index 19. So putting a node at index 20 is just not possible. That's why if the free pointer is pointing to something larger than index 19, then we can tell, okay, you know what, there's not enough space. And we will say tree is already full. Now, if there is enough space, we will ask the user to enter the data they want to add. So let's say console.writeLine, enter, and then we can take that as dim data to add as integer equal console.readline. So now we have to add our new node at the index of the free pointer, because again the free pointer is pointing to the index of the next free space. So let's say binary tree dot free pointer dot data equal data to add. And then now we have to initialize our pointers. This is because our new node does not have any left child or right child yet. So after we have assigned our node at the index of the free pointer, we have to increment our free pointer. The reason we do is because the free pointer is pointing to the index of the next free space. Now we have used the index of the current free space, so we have to increment it so that it points to the index of the new free space. So after that, what we have to do is we have to check if the binary tree is empty or not. Because if the binary tree is empty, then the first data we have to add is added at the root node of the tree. Remember my algorithm in the PowerPoint? If the binary tree is empty, we have to add our first data at the root node. Okay, how would we check if the binary tree is empty? Well, the root pointer points to the index of the root node of the tree. So if the root pointer is pointing to a null index, it means that we don't have a root node in our tree. Then it means that our tree is empty. So let's say if root pointer equal -1, so we have to first, let's say 2, check if tree is empty. So if root pointer is equal to -1, then it means that the tree is empty. 2a tree is empty. Then 2b tree is not empty. Alright, so if the tree is empty, what we have to do is we have to point the root pointer to 0. Why is the root pointer pointing to index 0? Well, that's because the first node in our tree is added at index 0. Remember, first node in our tree is added at index 0. So if our tree was empty, then the index of the free pointer would be 0 because the index of the free pointer is initialized to 0. Now, if the tree was empty, then the first node would be added at index 0. So first node in the tree is added at index 0. Alright, so, and then the first node in the tree is the root node, right? Now, if the first node in a tree is the root node, and the first node in our tree is added at index 0, that means that the root node is at index 0. And what the root pointer does is that it points to the index of the root node of the tree. So the root pointer points to the index of the root node. So the root pointer points to the index of the root node, and the root node is at index 0. So we would assign 0 to the root pointer. So I hope this makes sense. You can try to, think of all of this, and I would encourage you. But if you are in a hurry for an exam or something, you could just remember, if the tree is empty, then assign 0 to the root pointer. Alright, I'll just clear this off because we have more code to write. Alright, now what if the tree is not empty? Well, if the tree is not empty, we have to start by visiting the root node, and then we will visit the left, the right node, remember? So let's start by visiting the root node. So let's say dim current node as integer equal root pointer. So now current node has the index of the root pointer, and then we can declare a boolean variable called placed, dim placed as boolean equal false. So currently we haven't placed our value yet. Let's just say inserted then. We haven't inserted our value yet, so we can say inserted is false. Now I really want you to think of the presentation. In there, we started by visiting the root node, right? And what did we do with the root node? What we did was, we checked if the data we wanted to add was smaller or larger than the root node. So if the data we wanted to add was smaller than the root node, which is the node we are currently visiting, then we have to visit the left subtree. Okay? And if the data we want to add is larger than the root node, then what we have to do was we have to visit the right subtree. So now I hope you remember something. After we have visited the left subtree, there's one more thing we need to check. We need to check whether there is an empty space in the left subtree or not. In other words, we have to check whether the current node has a left child or not. If the current node does not have a left child, it means that the left of the current node is empty. If binary tree current node dot left pointer, if the left pointer of the binary tree was pointing to -1, it means that the current node does not have a left child. And if the current node does not have a left child, it means that there's an empty space. So we can add our node as the left children of the current node. This means that we have added the new node that we want to add as the left child of the current node. Remember, when we are adding a data to the left child, we're not adding the data literally. What we are doing is we're making sure the left pointer of the current node points to the index of the new node. So the index of the new node is indicated by the free pointer. Now, the left pointer of the current node points to the index of the new node, which means that the new node is the left child of the current node. So yeah, if there's an empty space, then we will make the new node the left child. But what if there is no empty space? No empty space. Well, if there is no empty space, and the current node has a left child, then what? Then remember, if the current node has a left child, we visited that left child, and we assumed that that is our new current node. And from there on, we started comparing and we started going left and right. So we can say current node equal binary tree dot current node dot left pointer. So now we have changed the current node. Our new current node is the left child of the current node we previously visited, and this will loop around. And here what we have to do is we have to say inserted equal true. So remember our third step in the binary tree. We have to repeat this process of like going to the left child, the right child, until we have find an empty space, right? So until inserted equal true, we have to loop this entire process. So let's put this inside the loop. Let's say while inserted equal false, as long as inserted is equal to false, we will be looping this. So let's put this here. And here you go. Okay. So now let's go over this one more time. If the data we're adding is less than the data at the current node, we will visit the left subtree. And when we visit the left subtree, we will check if the current node has any left children. If the current node does not have any left children, we can insert our new node as the left child of the current node. However, if the current node does have a left children, there is no empty space, which means that the left child of the previous current node is now our new current node, and we will repeat this loop again. So now let's talk about the right subtree. We'll do the exact same thing here. What we'll do is if binary tree, we will check if the current node has any right child. And if it does have a right child, then we will take that right child as our new current node. So let's go over this one last time. So the first thing we do, we check if there is enough space. If there is not enough space, we print out there is no space. So if there is enough space, we can move on. We ask the user to enter the data they want to add, and then we add that data at the index indicated by the free pointer. And then we check if the tree is empty. If the tree is empty, we initialize the root pointer to 0. And then if the tree is not empty, we go left or right until we found an empty place where we can insert the data we want to insert. Now we can talk about how we're going to search for an item in a binary tree. Searching for an item in a binary tree follows this simple algorithm. So let's say I want to search for number 8. First, we have to begin our search at the root node. So here. Next, we have to compare the data we're looking for with the data at the node we are currently visiting. So let's compare 8 with 12. Because 8 is less than 12, we have to visit the left child. Let's go to 5. Now all we have to do is we have to repeat this comparison process until we find the target or until we have nowhere else to go. I will explain what I mean by having nowhere else to go in another example later. So now we have to compare 8 and 5. the data we're looking for, 8, is larger than the data at the node we are currently visiting. So 8 is larger than 5, so we will have to visit the right child. And we have finally found our data we're looking for. I hope you noticed this pattern. Whenever we're searching for something or inserting something in a binary tree, we follow the exact same path. We check if the item we're searching or inserting is either larger or smaller than the node we're currently visiting. If the item is smaller, we visit the left child. If the item is larger, we visit the right child. And we compare it with the next node we are in. And then we will either visit the left or the right child. Alright, so let's try another example. In this example, we're trying to find number 15. So like before, we will begin the search at the root node. So we'll begin at 12. Now we will compare target with the data at the node we're currently visiting. So we'll compare 15 and 12. This time, target is larger than root node, which means we will visit the right child. Now we will repeat the comparison again. We will compare 15 and 17. 15 is smaller than 17. So we will have to visit the left child. And now we have finally found the data we're looking for. Let's try one last example. In this example, we're trying to find number 19 in this binary tree. As always, we will begin the search at the root node. Now we will have to compare target data with the data at the node we're currently visiting. So we'll compare 19 and 12. 19 is larger, so we will have to visit the right child. Now we will repeat the comparison again. We will have to compare the target data with the data at the node we're currently in. So we'll have to compare 19 and 17. Now 19 is larger, which means that we will have to visit the right child. Because 19 is larger than 17, we will have to visit the right child. But the right child does not exist, which means that I have nowhere else to go. Therefore, I can assume that the target does not exist in the binary tree. See, I have nowhere else to go. So I'll just say, yeah, it doesn't exist in the binary tree. So yeah, that's all about searching for an item in a binary tree. It is quite simple because it follows the exact same path as inserting an item in a binary tree. Now let's write a function to search for an item in a binary tree. First, let's prompt the user to enter the data they want to search for. Now try to think of the algorithm. We need to start our search by visiting the root node. Now let's first check if target is in the root node. So if target equal binary tree root pointer data. So the index of the root node is indicated by the root pointer. If it is, then we can just return root pointer. So what this is if target is the root node, we are returning the index of the root node. Now what I'm going to do is I'm going to declare a new variable. So let's say dim current node as integer, and I will initialize this with the root pointer. So current node now has the index of the root pointer. I'm going to create a loop. So do until binary tree current node dot data is equal to target. So we're going to repeat this loop until the data at the node we're currently visiting is equal to target. And from there on, we can actually just copy this pathway. Let's just replace target with data to add. And then let's first focus here. So let's go over this. So if target is less than the current node, we have to visit the left child. After we have visited the left child, if the left pointer of the current node is pointing to -1, it means that there is no left child. So this means that we have nowhere else to go. And what happens when you have nowhere else to go when you're searching for an item in a binary tree? Well, what happens is you have to say, control the right line, target is not. And then if there is a left child, we will take that as our new current node. The same goes here. If the target is greater than the current node, we will visit the right child. Now, if the right child does not exist, we will say data is not in the binary tree. Right child does not exist. And if the right child does exist, what we will do is we will visit the right child, and then we will take that as our new current node. And then we'll keep this process of going to the left, going to the right, until we reach a node which is equal to the target. So I hope this makes sense. Again, let me reiterate this again. We will start from the root of the node. If we found the data we're looking for at the root, then that's great. We can just return the root pointer. If not, then we have to start searching our search from the root node again. And then we will visit the left child if the data we're looking for is less than the data at the current node. And then we'll visit the right child if the data we're looking for is greater than the data at the current node. And then when we're trying to visit the left child, if the left child does not exist, that means that we have nowhere else to go. So we can say that target is not in the binary tree. If the left child do exist, we will visit that left child and we'll take that as our current node. And then we'll compare, if it's the left child we're looking for. If it's not the left child we're looking for, we will go left or go right again. We'll compare if the data we're looking for is greater than the data at the current node. If it is greater, we will visit the right child. If the right child does not exist, then target is not in the binary tree. If the right child do exist, we will take that as our new node. And then we'll compare that new node with target. If it is, then we will exit this loop. And after we have exited this loop, we can just return current node, which is the index of the target node. By the way, sorry, here I have to return -1. And then here also I have to return -1. So I can either return -1 if it's a function, or if it's a procedure, I can just write exit sub. So because it's a function, I'll return -1.